In this video, we present a simple hello example of artificial intelligence in C++ and CUDA. We will begin with a brief overview of the history of artificial intelligence, AI, okay, development. Okay. There are two main approaches in AI development. One is based on statistics and optimization. Suppose we call this SO. Okay. And the other one is based on neural networks, and we call this NN. Okay. The early beginnings of AI development started in the 1940s to 1950s. In the SO side, we had pioneers like Warner Fisher developing statistical methods for data analysis, which could be used in machine learning. And also George Danzig in 1947 developed linear programming and the simplest algorithm that laid the groundwork for solving optimization problems. For the NN side, in 1943, Warren McCulloch and Walter Pitts proposed a model of artificial neurons, and that laid the groundwork for neural networks. And in 1950, Turing test by Alan Turing was developed. It is a way to measure the machine intelligence. In 1956, the term artificial intelligence was coined at the Dartmouth Conference. The 1950 to 1970 were golden years for AI development. For statistics and optimization, we have the Bayesian methods developed. The methods make use of probability theory for inference and decision making. And also, we had hidden Markov models, HMMs, developed. Okay. They are used for speech recognition and time series analysis. For NN, Frank Rosenblatt developed perceptron. It is a simple neural network capable of learning. The perceptron is a supervised learning algorithm and learns from labeled data to make predictions and adjusts its parameters to minimize errors. While it is simple and limited in its capabilities, it laid the foundation for more advanced supervised learning techniques in AI and machine learning. The 1970 to 1980 is regarded as the AI winter. Okay. In 1969, two MIT professors, Minsky and Papert, published a book entitled Perceptrons. It discussed the limitations of neural network and claimed that it was impractical to use neural network to solve practical problems. So this basically killed the research in neural network. Okay. And there was very little funding in doing research on this area. Okay. Around this time, statistical methods and optimization continued to advance. So the expectation maximization, or EM algorithm, was developed. Also, support vector machines, SVMs, were also developed. The 1980s to 1990s are regarded as the revival period. But during this time, statistical methods became dominant. Neural network research was a niche field. It was serious research in artificial intelligence did not pay attention to neural network research. But during this time, a technique called backpropagation was popularized. Okay, it's developed by some researchers like one more Hart, Hinton, and Williams around the time 1986. Then it came to a modern era. There's the 2000s to present. Okay. In the early 2000s, large tech companies like Microsoft spent a huge amount of time on developing AI, but they solely concentrate on utilizing statistical and optimization methods to advance. So at that time, neural networks were still a niche field. However, the rise of big data and exponential increase in computational power, especially in GPU, brought together neural network statistics and optimization that make vast advancement in artificial intelligence. Okay. So we have the deep learning, okay, basically utilizing neural networks, okay, and coupled with optimization techniques like stochastic gradient descent, SGD, and backpropagation, okay, that make significant advancement. And also in probabilistic programming, we have frameworks like Pyro and Stan, okay, make it easier to build and infer probabilistic models. Then in late 2010s, the integration of optimization and statistics with neural networks led to breakthroughs. And then now we have the ChatGPT, DeepSeek, and many other models. Okay. They are mostly based on neural networks. Okay. So here we'll discuss the simplest model called perceptron. Okay. So perceptron is the simplest artificial neural network that one can have. And it is maybe the simplest supervised learning algorithm. The diagram here shows a forward propagation perceptron. Okay. So in a perceptron, we have inputs, okay, represented by say x1, x2, xm, okay, and another input with value 1, and then each of these is associated with a weight, okay, and one is associated with weight W0, okay, x1 associated with weight W1, W2, okay, and then we multiply these weights with the inputs, okay, and then sum them together, okay, as like this formula, okay. So sum I equals 1 to m xi times wi, okay. So this is the linear combination of inputs, okay, and then plus W0 times 1, that's the bias, okay. Some authors use B to denote it, okay, but here we use W0 to denote the bias. And this would be the argument of a nonlinear activation function that gives us an output y hat, okay, as shown in this diagram. Okay, so this goes for a nonlinear activation function that gives us a predicted output y hat. Okay. Now here is an example of activation function. Okay, that maybe it's the simplest. Okay, it is a step function. Okay, another popularly used activation function is the sigmoid function. Okay. Now here, in the step function, GA is equal to 1 if A is larger than or equal to 0, and it is equal to 0 otherwise, as shown in this diagram. Okay. So if A is smaller than 0, then it is 0. Okay. Otherwise, it is 1. Okay, the step function. Okay. Now there's how a perceptron learns. Okay. First, we start with random weights and bias. Okay. So these weights are random, W0 to WM. Okay, they are all random at the beginning. Okay. And then for each input, we compute the output using the current weights and bias. Okay. See here, W0 is the bias. Okay, so plus W1 times X1 plus W2 X2. Okay, we multiply this together. So this can be written as W dot X. X equals X0, X1, X2, pro Xn. Okay, X0 is equal to 1. Okay, and W0 is the bias. So the W dot X. Okay, and then this will be the argument. Okay, the dot product of 8. Them is the argument of an activation function, yeah. And that gives us a predicted output y hat. Okay. And then after we get this predicted output, we update the weights and the bias. Okay. So basically, we calculate, okay, the delta Wi and add it to Wi to get the new Wi. The delta Wi is calculated in this way. It is equal to eta times y. Y is the targeted output, and this is the predicted one, the one that we calculated from here, okay, times xi. So this gives us delta xi. So in this formula, eta is the learning rate. Usually it is a small positive value, this eta. Okay. And y is the desired output or the targeted output. Okay, the value that we use to train the perceptron. And y hat is the predicted output, okay, calculated from this formula. Now this perceptron can only learn linearly separable patterns. Okay. Linear separable means that if we plot the data on a graph, okay, then the data of the different types, different classes, could be separated by drawing a straight line, okay, or a plane or a hyperplane if in high dimensions. Okay. Now, for example, here is the output of an AND gate. Okay. So this is the x1, okay, axis, x2 axis. Okay. So you can see that when x1, x2 equals 0, 0, 0, n is equal to 0. The black here represents 0, black dot. White represents 1. Okay. So it's, so 0, 1 is equal to 0. 1, 0 is equal to 0. 1, 1 is equal to 1. So we can draw a line to separate the white from the black. Okay. We separate them into these two classes. The same for the all. Okay. So for all, we have 0 or 0 is 0. 0 or 1 is 1. 1 or 0 is 1. 1 or 1 is 1. Again, we can draw a straight line to separate the white dots from the black dots. Now, this is the exclusive OR. Okay. 0 exclusive OR 0 is 0. 1 exclusive OR 0 is 1. 0 exclusive OR 1 is 1. Okay, 1 exclusive OR 1 is 0. Okay. Here we cannot draw any straight line to separate the black from the white, no matter how you draw it. Okay. You cannot separate them. Can you classify them using a straight line? Okay. So that means the perceptron cannot be used to train an exclusive OR gate. Okay. Now this diagram shows how a perceptron after training could be used to represent an AND gate. So we have x1, x2, okay, as our inputs. Okay, could either be 0 or 1. W1 is equal to 1, W2 is 1, and then the bias is negative 1.5. With these values, when you put that into say this equation, okay, then you get the AND gate values. Okay. Now, as we just mentioned, a simple perceptron could not be used to train patterns that are not linearly separable. Okay. If we need to train the data that are not linearly separable, we need to use a multi-layer perceptron, okay, or MLP. Okay. Now here, this diagram shows a simple example of multi-layer perceptron. So we have this x1, x2, x3 inputs, and we have an input layer, and then this feed forward to a hidden layer, and from this hidden layer we have an output layer, okay, and that generates our output. Okay. But here we don't consider any multi-layer perceptron. We just discuss a very simple perceptron. Okay, so we'll give you a C, C++, and CUDA implementation of a simple perceptron that we call it Hello World perceptron. Now this is a C, C++ implementation of a simple perceptron. Now let's copy and paste this into a file. So we copy this and paste it into this file, perceptron.cpp, okay, and we save it. Now the implementation here is straightforward. Okay, basically it implements this formula. Okay, the formula is here. Okay. So here the W are the weights. The weights, the W is here. Okay, and X are the inputs. Okay, and N1 is N plus 1, because we have N plus 1 weights and N plus 1 X values, with W0 being the bias, and X0 is equal to 1. Okay, so totally N plus 1 values, and we call that N1. Okay. And so this is the constructor. Okay. So we set N1 to be the parameter nx. We pass in the number of x values, okay, and then they pass in the weights. Okay, so we create this array W to hold all the weights. Okay. So these are the private members. Okay. And we define an activation function, okay, which is a step function. The step function that we mentioned here. Okay, if it is the value, the argument here, if it is larger than or equal to 0, then it is 1. Okay, otherwise it is 0. Okay. And now this is the predicted output. Okay, to get the predicted output y hat here. Okay, so we basically sum all the value products, okay, of wi, xi. Okay, we sum this, okay, from 0 to n. Okay, so we get this basically w dot x. Okay, and then we put this into the activation function. This activation function, and the return the value is our predicted value, or the y hat here. Okay, we call it y1 here. Okay, so we return y1. So that's the predicted output. Okay. And then we need to do the training. Okay, so basically the update here. Okay, so we pass in the data x values, x data. We have a set of x values, okay, and this y holds the corresponding output value, this y, the desired output. Okay, and eta here is the eta value here. Okay, the learning rate. Okay, is a small positive value. Okay, the learning eta, and then the number of samples is the number of different input sets. Okay, so basically the number of different data sets in X data. Okay, in this array. Okay, and then the output. Okay, outputs here is the number of times of training. How many times we want to train the perceptron. Okay. So here, so we have a for loop. Okay. We train that many times. M equals 0 to m smaller than apples. Okay, increment it. Okay. And for each set of data, so k equals 0, k smaller than number of samples, increment k. So x point to the appropriate data. Okay. So the starting point is x data. Okay. So this is an array, but one set of data occupies n1 positions. Okay, so that's why in each training we increment this. Okay, so y1 is the predicted output, the y hat here that we just mentioned. Okay, and then the error is the y minus y1 here. Okay, and so we have to multiply this by eta, okay, and also xi. So here eta times error times xi, okay, and we get delta wi, okay, so dwi, okay, and then we update the weights. Okay, so wi equals wi plus dwi. Okay, basically the implementation of this formula. Okay, so we train this for different sets of data. Okay, and for that many times. Okay, so pretty straightforward. And here we have a function that prints out the ways. Okay, the destructor deallocate the memory allocated. And here's an example. This is the training data for an AND gate. Okay, so we have 4 sets of x. Okay, so x0 is always 1. Okay, and so we input 0 0 0 1 1 0 1 1. Okay, for x1 x2. Okay, and then these are the target outputs, or often referred to as labels. Okay, so 0 0. Okay, we get output 0. 0 1 output 0. 1 0 we get output 0. 1 1 the target output is 1. Okay, and the ways you can start with some random values. We just randomly put that to 1 1 1. Okay, and this denotes that we are doing with AND gates. Okay, and so we create a perceptron with say this 3 values. Okay, 3, and the w, the weights, okay, that we pass in, the weights here. Okay, and so this train that with this input sets of data. Okay, and the y. Okay, and the learning rate eta 0.1. Okay, and then 4 sets of data 1 2 3 4. Okay, and we train 10 times. Okay, so there's the train function. Okay. So after the training, that means we get a set of w values. Okay, that would operate like an AND gate. Okay, so we get like this figure. So it's okay. So we have a set of w values that would give us the AND gate function. Okay, so we test it. Okay, so we use this. Okay, x0 is always 1, x1 are x2 are inputs. Okay, basically and this is 1 and shift this y1, so we get 0 0 0 1 1 0 1 1. Okay, and we print out the output would be the x value and then the predicted output from these weights. Okay. So we get the final weight. Okay, with that w. Okay, we get the predicted output. Okay. So now let's try to compile this program, okay, and see if it works. Okay. So we compile this G++ perceptron ISO. Maybe call this N. Okay. And then we execute. So we compile, we execute. So you can see that we print out all these values. 0 and 0 is 0. So that's the output is what we get from the predicted output. Okay, and 0 1 is 0, 1 0 is 0, 1 1 is 1. Okay, and these are the ways we get. Okay, and print out this message, hello AI world. And now if you change the initial weights, then the final weights could be different. Okay, so that means the solution is not unique. For example, we can change this, say, the bias to be -1 to begin with, or -1.5. Okay, so closer to this example. Okay, let's make it -1.4. Okay, save it, and now let's compile this. Compile this again. Okay, so you can see that again we get the same results. Okay, so well, that's we start with the white values. Okay, so that's what we got at the end. Okay, so the solutions are not unique. Okay, and now suppose we change this data. Suppose we try a OR gate. Okay, so this maybe we copy this. Don't want to destroy this. We copy perceptron to a perceptron. One. And we change the data. So change this for an OR gate. Okay, the inputs are still the same, but the target outputs will be different. For OR gate, 0 or 0 is 0, 0 or 1 is 1, 1 or 0 is 1. Okay, 1 or 1 is 1. So this will be our OR perceptron. Okay, and now let's compile this. One or okay, so we compile and we execute. So again, you can see that we get the correct value. 0 or 0 is 0, 0 or 1 is 1, 1 or 0 is 1, 1 or 1 is 1, and then these are the ways that we have. Okay, and now suppose we try to do that for exclusive OR. we discussed that it won't work for exclusive OR. Now let's see. The exclusive OR, 0 exclusive OR 0 is 0. 0 exclusive OR 1 is 1. 0 exclusive OR 1 is 1. 1 exclusive OR 1 is 0. Okay, so that's exclusive OR. And now I train that with these targets. Okay, so now this becomes exclusive OR, and so you can say that it didn't work. Okay, so they gave us the wrong results. Okay, so because it is not linearly separable. We cannot draw a straight line to separate the zeros from the ones, okay, for this case. But for O and N, we can do that. Okay, so it fails to train these kind of patterns. Okay. In the CUDA implementation, to enhance computational efficiency during neural network training, we use one thread to update one weight in parallel. And this could accelerate the training process. To achieve this, we just need to make minor modifications to our C++ program, as shown below. We define an external function activate to be the activation function. Okay. This activate can be accessed by both the device and the host. We also define another external function, predict, that would do the predicted function output. So that's what we discussed before. And again, this could be accessed by both the device and the host, the CPU and the GPU. So this is basically the predicted output we discussed before. So we call this activate function, okay, to get the predicted output y1. Okay. And this is the kernel. Okay. Kernel function. It trains the perception. We need to pass in these parameters, the inputs, okay, the outputs, targeted outputs, okay, the weight, the learning rate eta, the n value, okay. There's basically the n1 we used before, okay, the number of samples, okay, and apples, okay. And now we use one thread to update one weight, okay. So we get rid of the for loop, okay, in our C++ program here, okay. So here we just use one thread to do all this, okay. But all now these updates are done in parallel. So that's what we have, okay, here. And so we make some modifications to the class perceptron. So besides this WXN1 that we used in the C++ program, we add these parameters, variables. Okay. So W size is the size of all weights in bytes. Okay. And num samples is the number of different input sets we discussed earlier. Okay. And DW is the device memory to store weights, and DY is device memory to store target outputs, and DX data is the device memory to store the samples data, the input data. Okay. And so we modify our constructor to be like this. Okay, we pass in again the NX num, the ways, the target outputs and inputs. Okay, again we set this N1 to be NX, okay, this N1, and num samples to be this num, and now the sample size would be the num samples times W size. Okay, this is for memory allocation, and output size is num samples times size of double. Okay, W size is given by this, okay, and W that stores the weight in the host, okay, in the CPU, okay, is allocated, okay, so memory. And so we set WI to be the weights that we pass in, okay, and then we need to allocate memory for the device. Okay, so all this is to allocate memory to the device, and then we copy the weights to DW, copy the Y to DY, copy input data to the DX data. All these are in the device side, okay, that used by the GPU. Okay. And this is our activation function. We just call the external function activate to do the value, to do the job. Okay, activate. And to predict the output, we also call the external function predict, okay, to do the job. Okay, this predict is also used by this training function. Okay. And then now here is the class train function that trains the perceptron. We pass in the parameter eta and apples only, because other parameters has been obtained from the constructor. Okay. And then we train the perceptron, okay, with one block and N1 threads. Okay, or the number of ways plus the bias, okay, N1. Okay, and then we pass in the data that we have, okay, and so we call this, okay, the kernel to do the training, okay, that does the training or the update in parallel. And then after the training, we need to copy the device data back to the host array W. Okay. And then our destructor perceptron, okay, would free all the device memory allocated. Okay. So in the main, we just need to change our constructor to include the new values, okay, W, Y, and inputs, and then train the perceptron using this data. Okay, now let's try this out. Now let's copy our perceptron.cpp to perceptron.cu. Okay. So this was our C++ program. Now we changed that to CU. Okay. And we delete this. And we copy and paste this part. Okay, starting from here. To here. Okay, and We also need to change the training and the constructor. So we copy this. And paste it. So this is our complete program. No change for others. Okay. The complete program for the perceptron that trains an AND gate. Okay. So the only thing new is here. Okay. Here's one thread to update one weight. Okay. All these are done in parallel. Okay. And let's save and compile it. Okay. So we say nvcc perceptron.cu -o perceptron. So it compiles and we can execute it. Okay. Again, we get these results. Okay. 0 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0, 1 and 1 is 1, and these are the weights. Okay. So this is a very simple example, or you can call it a hello world example in artificial intelligence written in CUDA. So if you think that this video is helpful, so please give it a like. Thank you for watching. I'll see you in the next video. Bye.